Welcome back, everyone. Today we're going to be looking at another envelope-controlled effect, kind of like a compressor or a noise gate, but this time it is what's called an envelope-controlled filter. Sometimes it's just called an envelope filter. And the way that an envelope-controlled filter works is that the cutoff frequency of the filter that's applied to the guitar signal is dependent on the envelope of the guitar signal. And the specific circuit that we're looking at today is going to be the MuTron 3, which is a very classic envelope-controlled filter from the 70s. And we're going to take a look just at the signal path here, and we're going to break it up into three parts. So the first part is our input buffer stage here, which is this box. Then we have the actual filtering portion, which is this big box here. And then we have the envelope follower, which is this section down here. Okay, so three basic blocks that make up our circuit. So we're going to start by walking through this. And so first we're going to take a look at our input buffer here. So this input buffer is actually not unity gain. Okay, you can see that we are coming in on the non-inverting terminal, which means that this is an inverting op-amp gain stage. And we know with an op-amp, with an inverting op-amp gain stage, that the gain is proportional to the ratio of our feedback resistor and our input resistor. And so what we have here is a potentiometer on the input that is going to change what the resistance is coming into our first op-amp stage here. And that resistance can go anywhere from 3.3K up to essentially 1 mega ohm, and we have 120K resistance here in the feedback loop, which means we can get up to about 40 times larger, or we can go all the way down to about 10 times smaller. And we do have a resistor and capacitor combo here off of the non-inverting terminal that provide a little bit of filtering. We have a very large DC blocking cap on the input. These really large capacitors on input and output are very common of a lot of 70s effects. It's not strictly necessary, but it makes sure that you're not getting rid of any bass frequencies that you might want to be holding on to. In our feedback loop, we have a very small 10 picofarad capacitor, which just provides some high frequency stability. And with that, we have our input stage. So it serves to add gain and to buffer the signal so that we can then split it between our filter and our envelope follower. Now, the highlight of this circuit is going to be this filtering section, and this topology here is what is known as a state variable filter. What that means is that it is a resonant filter, and we can actually tune each of the different quantities or the different parameters or states of the filter independently, meaning the frequency, the Q, and the gain can all be tuned independently by changing values of components in this filter. Now, the way that it gets used here is as a way to give you each of the three main filter topologies from a single circuit, meaning you can have a high pass filter, a low pass filter, and a band pass filter, and you can have those all at the same time if you want. So we're going to dig a little bit more into this. We're not going to get really into the nitty-gritty. There are some really great articles about the state variable filter that you can go read on the internet, but I am going to talk a little bit about how it works here. So our input signal comes in, and it's going to get filtered, and then the filter goes to the output. Okay, that's kind of the big picture here. But now let's take a look at this. Our first um, so our first stage here is actually a summing amplifier. Okay, and this summing amplifier is summing the high pass filter and the low pass filter in on the negative terminal, like this. And then it's subtracting from that our direct response and our bandpass response. Okay, when you have a summing amplifier is always going to be inverting. And so when you put something on the positive terminal or the non-inverting terminal of a summing amplifier, you're actually subtracting that signal out. Okay, so the way to kind of think of this is that we are summing the high and low pass here, we're subtracting the band pass here, and because of how that ends up happening, each of these taps allow us to be able to choose what kind of filter it is that we want. In the MuTron pedal, there's a three-way switch, just like this one over here, that's your mode switch, and it can be low pass, band pass, or high pass. And it's just selecting which of these 3 points from the filter it's using. Okay, so when we have our state variable filter, we have this summing amplifier here, but the key to this state variable filter is that it's then followed up by 2 identical low pass filters. Okay, that's what this guy right here is. Okay, we have a resistance that comes in on our non-inverting terminal, and we have a capacitance in our feedback loop, and this is just a low pass filter. Okay, and so we cascade 2 of those in parallel, or in series rather. Cascading is always in series. So we cascade 2 identical filters in series, and we send one back onto the positive terminal, one back onto the negative terminal, and that, through the magic of all the mathematics there, which I'm not going to go through and show how the transfer functions all shake out and everything, but by virtue of how we're combining everything at this summing amplifier and the low pass filter action of each of these op amp stages here, we get each of these 3 phases, or each of these 3 filter topologies, filter responses. Okay, now if we had just static resistors here, then our filter would be at a fixed frequency. Okay, because we would have fixed resistors and fixed capacitors, and our filter wouldn't change at all. What makes this filter change with our envelope is the fact that we have these LDRs that are in parallel with these resistors, which means that we are changing the resistance. And when we look at the cutoff frequency calculations for our different filters, the resistance and the capacitance determine what our cutoff frequency is. So as we change the resistance with these light dependent resistors, with these LDRs, we are actually changing the filter cutoff frequency. Okay, and so we're not going to look at the envelope follower just yet. A couple other things to discuss in the signal path, but keep in mind that these LDRs are what actually make it so that we can vary the cutoff frequency of our filter, which gives it that moving kind of quacking sound. Another thing that you'll notice is that in the feedback loops of our 2 low pass filter stages, we have a capacitor tied to a switch. Okay, this is the range switch, and because we don't really have variable capacitors that are cheap and commonly available in a wide variety of sizes and everything, using a capacitor on a switch like this is an easy way to change the range for the cutoff frequency. You can see that we have 1.8 nano that is always in there, and when we connect the switch to this capacitor, then we are adding another 2.2 nanofarad for a total of 4 nanofarads in our feedback loop, which is going to effectively shift our cutoff frequency by a factor of 2. Okay, and it does that to both of these feedback loops, because in order for this state variable filter to work the way we want it, these two stages have to be identical. So this is a DP/DT switch here. Okay. The other thing is that the amount of feedback from this bandpass stage that we put in here is going to change how much of this bandpass response we are getting rid of. So they have the control on the MuTron labeled as peak, right? And so basically what this means is this is kind of changing this is going to change the resonance of your filter. And so changing this is going to change how the filter sounds. And we have a static resistance here so that we never go to 0, but we can go anywhere from 12K up to 162K total resistance in this feedback loop. And you know, the more signal we let through, the more of this bandpass response gets subtracted out, and that changes our response there. Once we have selected which of the three filter responses we want, that comes through a non-polarized 15 microfarad capacitor, which is pretty big here, and a 560 ohm resistor to the output. Because this is a vintage effect, you will notice the lack of pull-down resistors on input and output. But, you know, with our modern knowledge, we would put those in there just for safety's sake. So now that we know kind of what this state variable filter is doing, we're just going to take a quick look at our envelope follower. The envelope follower, as we learned from the noise gate and also from the compressor videos, simply seeks to change our incoming signal into some kind of a very slowly varying voltage that we can use to control something. In the noise gate, we used it to control a JFET to either gate the signal or not gate the signal, and in the compressor, we would use it to attenuate our input signal if the signal got too loud. In this case, what we're doing is we are going to use the strength of the input signal to change the resistance of our LDRs so that the strength of our input signal is going to change the cutoff frequency of our state variable filter. So the way it does that is we come through a DC blocking cap here. We come in on the inverting op-amp terminal of this first op-amp here. And we have these two diodes, one in the negative feedback loop and one off the output before we have this 1 meg feedback loop here. And this arrangement right here is what is called a precision half-wave rectifier. So it takes our signal that varies between, you know, plus and minus voltage, and it's going to turn it into something that varies between 0 and some positive voltage, okay? And once we have a half-wave rectified signal, we can then smooth it. And we smooth it into essentially DC through these components here off of the output. Okay, we are forming a filter. And what's happening is this cap is charging and discharging depending on how strong the signal is coming out. So what that serves to do is it smooths our lumpy half-wave rectified signal into a very slowly changing signal. So the attack time for the filter is going to be determined by this resistor. That's going to govern how fast we can charge this capacitor. The bigger this is, the slower our capacitor is going to charge, meaning the slower our attack is going to be. If we make it smaller, it'll be a whole lot faster. But when we don't have any signal coming through here, then this capacitor is going to discharge through this resistor to minus 9 volts, which is our which is our negative voltage reference in the circuit. And so this resistor, R16, is actually going to control the decay time of the filter. The smaller this is, the faster the capacitor is going to discharge, and the faster our decay time is going to be. And if we make it larger, then the cap discharges more slowly, and we have a slower decay time. And once our capacitor here has kind of smoothed things out for us, we then come into this op amp stage, which is used to drive this LED. And this LED shines on our two LDRs. In the vintage unit, this was a single Vactrol that has one LED and two matched LDRs inside of it. We can make our own with a single LED and two LDRs if we want, or we can try and find a more vintage correct type device. It doesn't really matter as long as these LDRs are well matched and exposed to the light equally. And so we have 120K here and 120K here, which means that we're just trying to drive the LED based on what our input voltage is. This resistor here, you'll notice it doesn't have a value, and that's because it depends on the specific LED in our device. That's something that you would kind of dial in for your LED and for the desired range that you want for your envelope filter effect. So, you know, I didn't put a value there. The actual factory schematic actually has a note saying it depends on the device. And the last thing that we have as it relates to our envelope follower here is this drive control. Okay, drive is this control really governs whether or not the filter sweeps up when the signal gets stronger, or if the filter frequency sweeps down when the signal gets stronger. Okay, and the way it does that is first it switches a resistor in parallel here on the input, which means that we are reducing the input resistance to an inverting op amp gain stage, which means we are increasing the gain of this first stage. But then you'll notice that instead of having this be just this normal feedback loop, it then changes to having our positive terminal being tied to this reference voltage right here. 9 volts, ground, 180K, 120K means that we have just slightly less than 4.5 volts. We've got around 4 volts right here. Because this is a plus 9 volt to minus 9 volt bipolar power supply circuit, that actually means that we are skewing the direction at which this op amp stage wants to idle. If you remember, an op amp wants to make sure that the voltage at each of its 3 terminals is the same. And if we take one terminal and we artificially tie it to a high voltage or an offset voltage, then what that's going to do is it's going to skew everything else the same way. And so what that does is it makes it so that our LED is either off until the envelope makes it turn on, or it's on until the envelope is strong enough to turn it off. It's just kind of changing the direction that that our light lights up relative to the input signal. Okay? But once we have all of that, all of the signal through our envelope follower doing all of this stuff, then its whole job is just to change these LDRs. And this is an example of an envelope controlled filter, which is really just a more specific term of a voltage controlled filter, which is what our state variable filter right here is, that is being where the control voltage is being determined by the envelope. Now, hopefully that's been useful to you. I tried to make it relatively quick without glossing over too many details. If you want to learn more about this, RG Keen has a great article at GeoFX, and there are a couple of good articles on the state variable filter. I'll put links in the description below. But until then, take care. We'll see you next time.